Sarang.
Hi, Bhumik.
Hi, Rohit.
Hello.
Okay, so let's start. If anyone else is going to join, I'm sure they are going to pour in. So we covered the basics of probability yesterday, right? We have cleared the definition. We have cleared what is a random experiment. We have cleared what is the sample space. We looked into what is an event and some math behind the probability. Now we will look into some few things related to these 5 points before we jump on to the next points. Before we started onto probability, we also looked into univariate or single variable analysis. Then we looked into what is a probability density function. It is not a distribution function, right? It is a probability density function. Then we looked into bivariate and multivariate analysis, the definition only. We not looked into the actual thing. Then we looked into how a frequency table is created, what all visualizations is actually possible out of a simple frequency table, and then what are the limitations basis which we started creating grouping of the data using bin. So that is also yet another type of frequency table which we created, which resulted into a better set of visualizations other known as histograms. From the histograms, we were able to figure out the probability density function. This all happened because of a single variable analysis which we did. So it happened because of the univariate analysis which we were performing. Okay. Now we will look into some of the rules of, let's say, probability, and we are also going to look into some mathematical operations which are possible in case of, let's say, probability. But before we do that, there are a few things that I would like to specifically mention to you before we go ahead. Okay, so there are a few things. This is what we have already looked into earlier, and that needs to be clarified first before we move ahead. So first of all, we'll look into 3 different types of probability that we have. Okay, so ideal condition. Maybe I'll just remove this and say 3 types of probability. Okay, so the first type of probability is otherwise known as classical probability, also known as a priori probability. Okay, now this is seldom used in the industry. The reason why it is seldom used is because the purpose of this kind of a probability is only to see the effect of, let's say, probability. Example given, the examples that we have taken. Okay, like a rolling of a dice, or maybe the tossing of a coin. So these are the examples that we took yesterday. Now these are really not industry examples. These are like the toy examples that we have taken. So similarly, if I am doing some kind of a probabilistic experiment based on a very small set of data or a very limited set of data, which is only to look into some of the characteristics relevant to the probability. Let's say we are going to look into the rules of probability now. We are going to look into mathematics behind the probability now. So if I would like to prove some rule, or if I would like to really check whether that rule is valid or not, then I'm going to do this kind of a probability test. So basis the test, this probability is known as a priori or classical probability. This is, as I said, seldom used in the industry. In industry, almost nobody uses it. It's only for some of the impractical or testing kind of a purposes. So research, yes, but not for any practical uses. The second type of probability which we have is known as empirical probability. Okay, now before I say what is empirical probability, I would also like to say something else about the probability. Example given, we looked into some basic math of probability. So I'm going to say basic math of probability. Here, I was interested into a certain kind of event. And that event was if I can get a 6 when I roll a die. So I'm going to roll a fair die where the event space is 1, 2, 3, 4, 5, 6. And there are 6 items in the event space. And then I am only interested about the probability or the chance of getting a 6 out of rolling a die. And we saw that it is as simple as definition of probability says it is a ratio of the number of favorable outcomes, also known as the event. So I'm going to write that text here. So the favorable outcome. Yeah, so it is either known as event, it is also known as favorable outcome. So the count of favorable outcomes as opposed to the sample space, or the sample space is also known as all possible outcomes. Okay, so this is what we did. We simply divided the two numbers, we got the probability, which is approximately 0.16. And then we said that if I multiply that number with 100, I can tell you a percentage. So if somebody asks me what is the chance of getting a 6 if I roll a fair die, I'll say there is usually a 16.67% chance. Okay, because there is a 1/6 chance that you will get a 6. Now the rule that I wanted to tell you is what is the probability of getting a 1? Okay, if the probability of getting 6 is this, then the probability of getting a 1 is also this, right? It is also 1/6. If you do the calculation, you will come to know probability of getting a 1 is 1/6. Probability then if you calculate of getting a 2 is also 1/6, and so on and so forth. Now why I am doing this is because if I take the probabilities of or individual probabilities of individual events or individual probabilities of the possible set of events, give me a minute. Huh. So if I take the individual probabilities of each and every of those events and I do a sum, then the sum of all of the individual probabilities will be equal to 1. Okay, this is a golden rule. This rule is not going to change. If there are certain set of sample events which are there as part of or interesting events or favorable outcomes, part of all possible outcomes, I take the probability of each and every item of the possible outcomes. Ultimately, I get 1. So I add up all the probability, I get a 1, right? So this is what the value is. Now, keeping this in mind and keeping the division that we have done over here, empirical probability is the practical purpose implementation of probability. What I do, I want to know what is the probability of an O positive person or a person with blood group O positive, for example, getting contracted with COVID-19. So I go out on the road, I ask each and every person as much as possible in my area, at least. I cannot go into the entire country. By the time I travel the entire country, the problem may already be solved. So I just want to take a small sample. In this case, population is all the population of our country. My sample is only the area in which I stay. I go out in my society, starting from my own housing cooperative society, which is here. Then I go outside on the road. I start asking questions to people. I ask them, sir, I'm doing a survey on COVID-19. I'm trying to find out if there is a relationship between your blood group and the probability of you getting COVID-19. So, because this is a so important thing as of date, then people may agree to participate as well. In which case, I ask them, are you O positive or no? And then I ask them whether they have any symptoms of COVID-19 or not. So I record all of this, let's say, in an Excel sheet while I'm carrying my tablet, and I go to 200 or 500 people. So this is what I am doing as part of an experiment. So whatsoever data that I could collect is, or the people whom I could ask this question, otherwise creates my random sample. I have not created any stratified sample here, right? I have not created any systematic sampling. I have not done any stratified sampling. I'm simply going out on the road asking people. Okay, maybe I like doing random samples. So a random sampling technique I've used, I've gone out into the market, I've asked people their questions, I've recorded the answer. I come back home and then I find out the probability. Okay, then I try to find out the probability. My favorable outcome in this case will be what? I don't have COVID-19. Okay, so let's say there are 500 people I've scanned and there are 350 or 415 people who does not have any symptoms at all related to COVID-19 and they are O positive. Okay, then I will say the probability of somebody not having okay, not having to contract a COVID-19 virus problem is 415 divided by 500. So there is a chance of 415 divided by 500, or I can convert that fraction into percentages by multiplying it by 100. That is the percentage chance of you not contacting COVID-19 if your blood group is O positive. Okay, this is just a very dummy and a very baseless kind of an example. I don't think WHO claims this. So this was just to prove the point how I'm going to actually do empirical probability experiments. So if I'm going to actually do an experiment like this without doing any falsified statements and without saying that yes, I've done my job as a statistician, rather I actually go out on the road and I do a sampling and I note down the records and I do these kind of things, that's known as empirical probability. Okay, because the probability that I'm finding over here is entirely data driven. That is the reason why 90% of all experiments, all possible experiments in the industry are done using empirical probability. Wherever there is data, people will first go to the data. Any statistician will first of all go to the data. But let's say, let's take a different example. Let's say I'm trying to launch a mobile phone. Okay, there is a big craze going on in India right now that we should be boycotting all the China products. So let's say there are a lot of phones which are created or manufactured or also assembled into China. I want to remove all the dependency. I would like to create their replacement. So I would like to create a new mobile phone. That mobile phone is the first brand or the first item that my company has ever produced. Let's say I'm creating a startup company. I'm going to start a new company. I'll take some fund from my friends, from the businessmen I know, or maybe from the government as well, because government as of day today is also funding startups. So I go to people, I collect the money, then I start my company who is going to produce a mobile phone. Now my question is, in this case, I don't have any historical data. I can only go out in the market and ask for their feedback. People may definitely be saying a no to the answer whether they like my phone or not, because they don't know what the phone looks like. The phone is still into production, right? There is no version of the phone which is there in market. I'm still planning to launch a phone. Maybe I'm going to launch the phone tomorrow, or maybe next week on Wednesday. So which means I have no previous data, I have no historical evidences, in which case I have no other option but to call a subject matter expert. So let's say Sarangs is a subject matter expert. He has looked into a lot of launches when it comes to mobile phones. He knows what is the Indian market or how things are going to work when it comes to the Indian market, when it comes to smartphones. So this person comes now. Aranx has been called. Okay, he has not come by himself. Okay, this is a very important thing. He has not come by himself. I have called him. I have called a subject matter expert, and that subject matter expert is essentially going to give a chance not based on data but based on previous experience. That is known as subjective probability. Okay, subjective probability is when the experimenter brings a subject matter expert or tries to apply the subject matter expertise on a certain subject or a certain scenario basis. He or she doesn't have the luxury of doing any statistics on top of data because the data at all doesn't exist. So what will I do? Right? So these are the three types of probability. First of all, classical or a priori probability, seldom used, as I said, hardly 0.01%. Then there is empirical probability, which is 90%, and subjective probability will obviously be 10% because there will be at least 10 to 15% cases where you don't find any data. Right? Now, once I have defined the type of probability, let's also define something else, which is known as the types of events. Once I have defined the types of events and the types of probability, then I should be able to do the mathematics on top of, or the rules which are on top of the probability. Because when you look at the types of events, you will by itself come to know what kind of mathematics will be applied on them. Okay. Now, just a word of caution. In this case, when I talk about the types of events and then the mathematics which is going to follow, I am going to assume that you are somewhat aware of set theory. Okay, or how the set notation works, because set notation or one part of set notation is going to be used. But then, just to relieve the pressure, anything and everything which is there into probability can be represented using the basic math functions. What I mean by that is addition, multiplication, division, are, or in some cases, let's say subtraction as well. So these are the four basic operations by means of which you can define any probability scenario. So any probabilistic experiment, any experiment which you are trying to do to find out a probability, can be explained only by the permutation and combination of these four operators. So that's one thing. The second thing is, sometimes we will need to know how to look into a problem when it needs to be looked into from a perspective of chances, or when, let's say, there are a lot of items which are there on my plate, and I need to decide how many items will be picked up or in what fashion they will be picked up and so on, in which case some knowledge, okay, some basic knowledge of it's a permutation and combinations will be required as well to understand what is going on. So maybe when we look into those mathematical areas, we are going to touch them. Let's say when we do, let's say, linear algebra, we are going to touch them once more. But here I will simply assume you have at least some basic knowledge what is permutation, what is combination, and what is plus, minus, multiply and divide. That's all you are going to need. You don't need anything else other than some notations which are used into set theory. Okay, so let's start with the first type of event. This is the most common event, and this is the event where there is going to be a fight. Okay, this event is known as mutually exclusive events. Mutually exclusive events, okay, are otherwise known as cases where I have, let's say, event A and I have event B, and these two events A and B, okay, are actually enemies of each other, which means if A is going to occur, B cannot occur. If B is going to occur, A cannot occur. Okay, let's say I have a deck of 52 cards. Okay, a deck of cards contain how many? 52. So in a deck of cards, I have how many cards? 52 cards. Okay, in those 52 cards, there will always be kings and queens. So there are four types of cards which are there: hearts, spades, diamonds, like. So four types of cards are there. Each type of card has a king and a queen. So how many kings and queens are there? Two each type. So there are four types. So there are 8 cards which are kings, kings, and queens. Right? Out of this, let's say my favorite color is spade. Okay, so I take spade. Okay, I take the spade type and I select the king and the queen. Okay, I have the king and the queen card in my hand. Randomly, if I ask Rohit to select a card out of these two cards, it can either be king or queen. Okay, it can never be both, or it may be king, it may be queen. We don't know that, but it will either be king or queen. So this word is going to be important here. Okay, the most important word over here is this. It is either going to be king or queen. When you look into the mathematics, that or thing is going to come into picture. Okay, the mutually exclusive events are two events A and B. They are said to be mutually exclusive if occurrence of A precludes the occurrence of B. Right? So if event A occurs, B cannot occur, and so on. Okay. The second type of event, which is quite important for us, is known as independent events. Okay. Please note the events that we are talking about over here are just few types of events. We are not going to talk about all the types of events because we don't need them. We just need a few types of events to understand a few types of events, because without understanding them, we won't understand the machine learning or data analysis types which are based out of probability theory. So that is the reason why we are learning them, or otherwise there is no need. We don't need to be a great expert into probability. We need to know the basics so that we can understand at a later stage what those analysis techniques are going to do. Now, so independent techniques are what? Independent events, I'm sorry, independent events are what? Again, let's say I have two events, A and B. A and B are called independent events if the occurrence of A is by no way influenced by the occurrence of B. Right? So occurrence of A is not affected by occurrence of B. Okay, if you have any such case where you have a case where you have two events and one event does not affect the uh, uh, the outcome of another event, right? So that is the place where you call that as an independent event. Okay, for example, okay, let's say let's take an example. Okay, so independent event is going to be, let's say, uh, landing on heads after tossing a coin, or rolling a 5 on a 6-sided die, right? So somebody, let's say I am doing a coin tossing. Okay, so I am having a coin in my hand and I am actually tossing it. In front of me, there is someone else. My friend is there who is sitting right next to me. He's playing some game with a die and he wants to play a 5. He's trying a lot, but the 5 is not coming. So he's doing an experiment and his favorable outcome is 5, or the number 5 on the side of a die. And what I'm doing is that I'm trying to simply toss a coin and I would like to see if there is a heads or not. These two events that we are doing together, okay, so what we are doing here together is landing of heads in a coin toss. This is, let's say, event A, and event B is where uh, uh, um, getting a 5 from a roll of 6-sided die. Okay, so these two events are known as independent events because there is nothing, absolutely nothing to do with a coin toss as opposed to rolling a die, right? So this is a very common example when it comes to independent events. Okay, there is one concept in probability which we are going to learn at a much later stage. Wherever it is really applicable, then only we are going to learn. That is known as independence. If you read anything of this sort onto the internet, please don't get confused between independent events and independence. There is independence between the independent events, but that does not mean that independence or the concept of probabilistic independence is the same as that of independent events. That is entirely different. This is entirely different. Okay. One more crucial thing before we progress related to independent events. Independent events are not affected by their or others' previous outcomes. Example given, I am trying to find a head. After some point in time, let's say I'm totally frustrated, I'm not getting any heads. So I'm now trying to find the probability of tails. So the previous experiment that I was doing to find event A was to toss a coin but to get a head. The next experiment that I'm doing is also tossing a coin, but I'm trying to get a tail, or I'm at least trying to find out the probability of getting a tail. I know that mathematically it will be 50%, so half of the time I should get it, but I am trying a lot. So the occurrence of tail is not affected by head, right? A and B are independent events with each other, but in themselves also, inside themselves, or in their own world of experiment also, the previous event does not affect the next event, right? So that's what is an independent event. Now we have two more types of events which we need to cover, and then we can go ahead. First of all, we have an event known as disjoint event. These are the events which cannot occur at once. Oh, sorry. I think I needed to write the definition as well. So mutually exclusive is what? When one event occurs, the other cannot. Okay, this is the definition. It's a simple definition. One is an enemy of the other. Independent, the occurrence of one event has no implications or effects on occurrence of any other event. Okay. Then I have an example of, or a case of disjoint event. Okay, events, two events. Okay, events, or I can say events. Okay, two or more events, not two. I mean, it is not related or limited to two. Two or more events which cannot occur at once. Okay, if there are any events which does not occur at once, then they are known as disjoint events. Okay, example given, it is raining heavily. Okay, around 2 days back, it was raining so heavily in Pune. Okay, drastic rain was there, drastic rain. We all got scared. When there was a rain, it was almost a post afternoon kind of time. Post afternoon is not a time when the sun is going to die or the sunlight is going to die, but I can assure you, you have not seen it. It was raining so badly, and it was so heavy, windy as well as rainy. It was not like the Amphan wave which hit the West Bengal side, but it was really, really very rainy, and we were not able to see any light at all. Which means that one event is a very, very heavy rain, and the other event is the chance or the probability of we seeing a sunlight, right? Even if it is a time when we should see a sunlight, in this case, okay, events do not occur at once, okay, because there is a heavy rain. I cannot see the sunlight. So these two events in this context are known as disjoint events. One thing that I've used the word context is just to tell you that each and every type of event is almost always contextual. Okay, it is going to depend on what context you are talking about, what example you have taken, what scenario you are in, or or what experimentation you are doing. So depending on the experiment, the definition of the event is going to change, or it is going to take the form of the examples. Not all examples are going to fit in all the kinds of events or all the kind of context. The last type of event, non-disjoint events. Okay.
Bomik, can I ask a question here?
Yes.
In disjoint events, when you say events which cannot occur at once,
Yeah.
so I mean, what kind of events you're talking about, like mutually or independent? Because in independent also events they cannot occur at once, right? Event A and event B.
No. Independent events. See, independent events is when, as I took an example. Okay, so my example said that let's say this is me, this is you. Okay, event A is being done by me, event B is being done by you, and we both are sitting on the same sofa and we are doing this. Or maybe we are sitting near to each other in our office, and we don't have any work. So you are doing, or I am doing a coin toss. You are doing a die roll. So these are two
Yes.
events which are independent of each other, not because they're happening or not happening at the same time. They're independent of each other because the outcome that I am looking for does not affect the outcome that you are looking for. So you getting a head or a tail is not going to affect whether I'm going to get a 5 or a 3 or a 2.
Oh, I see. So the outcome is not impacted
Exactly, exactly,
in order of the inference.
exactly. What is the
Okay.
event here? You see, this is the event space. The event space is when you toss a coin, you will either get a head or a tail, right? But you are interested, let's say, into getting a heads. So head is the event. Head is the uh, 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 otherwise known as the favorable outcome, right? So favorable outcome is head, but your favorable outcome, head, out of a set of head and tail, does not affect my favorable outcome, which is 5 out of a set of 6 numbers in a 6-sided die. So that is why they are independent events. Okay, but disjoint events is where I am doing something at the same time you cannot do the same thing. These are two different events which is going to happen. This is not like mutually exclusive event. Mutually exclusive event is when I did a single experiment. You see, here I have done a single experiment. I have a deck of card. Out of that, I picked up only the kings and queens. Then I picked up the spade king and spade queen. Then I am doing an experiment. The experiment is I have two cards in my hand. I'm not going to show which card is what to Rohi, and Rohi is going to blindly pick up a card. That card can either be a king or a queen. So it's part of a single experiment. In this case, when I'm talking about a disjoint event is one or more events, which means there are one or more experiments because one or more experiments are getting conducted at the same time. Where I am saying the conduction of one experiment is affecting the other by the thing that if one experiment is going on, the other will never happen. Are you getting my point? So let's say a football match, okay, a football game. A football game cannot
Mm-hmm.
be held in the same time in the same ground when you want to play rugby. If that same ground is
Oh, I see. I mean, in the same event,
right,
in
I
the
mean
same timeline.
in the same timeline or in the same, let's say, context. Yes.
Got it.
Let's say
Got
you
it. Got it. I actually confused in the sense that if two events like event A, event B, which
hmm,
are independent, if
hmm,
they can occur together,
yeah,
and so in that sense I got confused. But it's clear now. Quite
okay,
clear now.
okay,
Okay.
okay.
Thank
So non-disjoint events are simply the things that can actually occur, events which can occur. Let's not waste our time by taking an example here. You can yourself find out an example. It is quite easy. Let's just move ahead. We have 10 minutes left, so we will try to cover some parts of the mathematics. Let's see how much we can cover. At least we are going to cover a couple of important rules of, let's say, computation, and then we'll see what happens. Now, we have looked into mutually exclusive events, or we have looked into events which are exclusive of each other. So either one is going to happen or the other is going to happen. So if that is going to be the case, then basis this mutually exclusive set of events, there is a rule, okay, a rule that applies onto mutually exclusive event. And that rule is otherwise known as an addition rule. Addition rule is where from the set theory dimensions or the from the set theory text, I'm going to copy or I'm going to borrow the sign of union. So a set union to another set is represented by a sign language. I'm going to draw the sign in a moment. So I'm going to import or borrow that sign, and then I'm going to simply borrow the addition or the plain and simple addition in mathematics that I do, right? So how do I actually represent that is that, let me see if I can properly draw it here. Uh, so let's say there is an event A, and I'm trying to find out the probability of the event A. Okay, and then there is one more event which is event B. So in this case, I had two events, right? Either I have got a king or I have got a queen. So let's say king represents. So I'm going to write king is going to represent event A, and queen is represented by event B. So if two events are mutually exclusive, A and B are mutually exclusive in this case, I can write that A and B are mutually exclusive in this way. So if events A and B are mutually exclusive, they are represented by this set theory symbol, which is also known as a union symbol. Okay, so this union symbol represents the addition rule, which is applied on top of two mutually exclusive event, which says that it is simply the probability of event A summed up, okay, or do a plus sign here. So this is the addition rule. So we are going to use the plus sign. Addition of the second event, which is the probability of the event B. So if I take a sum of probability of event A and then I take a sum of probability of event B, then I get the probability of these two mutually exclusive events, or otherwise known as the addition rule. So let me put this into a different way. This rule says that the probability of the union of A and B, okay, union of A and B, somehow I am trying to make sure that A and B are now going to occur at the same time. Maybe I'm going to do two experiments. One experiment is to produce A and one experiment is going to be by B. Okay, so one experiment to produce A, one experiment to produce B will be done simultaneously at the same time. And then I would like to know what is the probability of these two events happening at the same place, which can be described by means of this addition rule, which is signified by this plus sign, and it is simply determined by the addition of the probabilities of the individual events, right? If A and B are mutually exclusive, I have to do multiple experiments because they cannot occur simultaneously. We have already seen this, right? Mutually exclusive event. In case of this example of mine, when I've only taken spade and kings and queens, in which I'm pulling one card. A union B is impossible, right? A union B cannot happen. In that case, I have to do more than one experiment if I would like to figure out, or I would like to conduct an experiment where I have, or where I see such kind of a possibility of having a union of two events which are by themselves mutually exclusive. So this is known as the addition rule. This is not only applicable on mutually exclusive events, it is a generic rule and it is applicable to all. The reason why I took the example of mutually exclusive events is that I wanted to specifically tell you, if the events are really mutually exclusive, be careful, find out if they are really mutually exclusive or not. That the presence of A is not going to let the presence of B happen. If that is the case, this is impossible that within a single experiment you can find A union B. You have to do multiple experiments. How you are going to conduct that is up to your, let's say, scenario or the assumptions or the limitations which you have and so on. But you have to do multiple experiments. That's why I specifically took that name. But addition rule that we see over here is simply the addition of one probability and other the probability. A probability of all such events is taken and then added up. Usually this is applicable on two events. I have seldom seen any case where there are multiple events. So I'm only going to represent this union thing with respect to two events only. I've never seen any mathematical representation where I have more than two events. So here I have two events. I'm doing a union because I want to know what is the probability of both of them occurring together at the same time, irrespective of the number of experiments that I'm trying to do, in which case it is a summation of the individual probabilities. Okay, this rule is known as the addition rule. Okay. Now, if there are events which will be intersecting events, okay, let's say I have two events. I have an event, let's say P. I'm going to take some, no, I can't take that in P. I have to calculate the probability. How can I take that in P? So let's take, I'm going to take some other name, let's say M. So I have an event M and I have an event N. Okay, so these are two events, some kind of experiment that I'm doing. Okay, and the experimentation is something like this. M is giving me results in form of these x's that you can see. Okay, so I have a lot of x, which is output of the experiment M. And then I have this experiment N, which is giving me a lot of y's. Okay, so usually there are a few y's which are overlapped with x's, and there are a few y's which are not overlapped with x's. There are a few y's which are away from x. In this case, I can clearly see that this is the set, approximately this is the set of my outcomes which was part of the experiment M, and this is the set of outcomes which was part of the experiment N. In this case, I have a common area. I have something which is in common. Okay, I have some part which I'm going to represent as this hash. This hash part is actually common between these two experiments. So maybe some of the outputs which they are actually producing are actually common. Example given, let's say I have a big bag and I have a lot of balls in there. I have three definitive types of balls. One ball is red, another ball has straight lines in them, another ball has crossed lines in them. Okay, so I have three types of balls: red balls, straight line balls, and cross line balls, so CL. Okay, what is the probability, or in this case, this area, right? This hashed out area can be a case where I have randomly picked up a ball from this bag, and that ball is not only R or red, but it is also having a CL. Okay. Now, as you can see, if it is having a CL, it is already having an SL. Okay, because these straight lines are already there in CL as well. The straight line is already part of the CL type of ball. So this is going to be the space where this is overlapping. Unfortunately, we don't have time. So let's continue in the next week. We're going to continue from where we have left. We have not looked into this topic right now. We have looked into addition rule, and we are still looking into addition rule only, and we are looking into a specific problem set. Okay. Have a good weekend. Let's talk on let's say Monday, same time. Thank you.
Thank
Thanks,
you.
Pamik. Have a nice weekend.
Same to you.